So let's move now to the second part of lesson 2, which is gas stoichiometry. So in gravimetric stoich, we use the molar mass because when we are moving from mass, when we are moving from moles to mass, the connection between the two is the molar mass. So when we move from mass to moles or moles to mass, what we are using here is a molar mass. In gas stoich, what we will use is molar volume. For the mole, so when we have volume to moles, we will use molar volume. Okay. Now, there are 3 conditions that we have to take into the consideration. Is when we have the STP conditions, standard temperature and pressure conditions, the molar volume is a fixed number, is 22.4. We dealt with that when we liters per mole, meaning that any gas at STP conditions will occupy 1 mole of that gas, 22.4 liters. And when we are dealing with, say, TP conditions, 1 mole of any gas will occupy 24.8 liters. So this is the molar volume on STP and SATP condition. Now, those numbers, I suggest you to write down into your data booklet at the last page of it so that you have them there. And when we have non-standard temperature and pressure, what we are using is the ideal gas law, which is PV is equal to nRT. Okay, let's deal now with some examples here. If we have hydrogen and oxygen, hydrogen and oxygen react to at 150 kPa and 19 degrees Celsius, then what we are doing is we are calculating the molar volume here, N. Okay, so what is N? In this case, what we will do is using PV is equal to nRT. So pressure is 150 kilopascal. Temperature will be 19 degrees Celsius plus 273.15 to convert it into Kelvin. And R is the constant, and we are looking what is the molar mass or volume, sorry, molar volume. So what is liters per mole? Liters per mole means V over N. What is V over N? So this will be RT over P if you manipulate it. Okay, so let's do this calculation. 273.15 plus 19 will be giving you 292.15 Kelvin. So now V over N will be R, that is 8.315314. And the units for it are kPa over, you know the units from times 292.15 over 150. So 8.314 times 292.15 divided by 150 will be 16.2 liters per mole. This will be the molar volume of the gas in non-standard conditions. Let's work now some examples here. So we have hydrogen gas is produced when sodium is added to water. What mass of sodium is needed to produce 20 liters of hydrogen gas at SATP conditions? So we'll start with a balanced equation, because every time that you're dealing with Stoich, you will start with a balanced equation. So liquid will give us 2NaOH aqueous solution plus hydrogen gas. Okay, what we are looking for is 20 liters of hydrogen, or what is given, and what we are looking for is what is the amount of sodium that is needed. Now, in the gravimetric Stoich, what did we write below? We wrote what is the molar mass. Now here we will write along with molar mass, we may need, which we may need or not, depend on the question. We will write the molar volume. So since we are dealing with the SATP conditions, the molar volume of hydrogen is 24.8 liters per mole. So start with what is given. 20 liters of hydrogen. This 24.8 liters per mole means 1 mole, and in this case of hydrogen, is occupying 24.8 liters of hydrogen. Or if 24.8 liters of oxygen are occupied, then we have 1 mole of hydrogen, not oxygen. So hydrogen, but it's for any gas. So now what we have is 2 ratios, the ratio 1 and the ratio 2. We start with liters of hydrogen, and we will use the ratio 1. So 1 mole of hydrogen is occupying 24.8 liters of hydrogen. So liters of hydrogen and liters of hydrogen is cancelled out. What do we have up to here? It's moles of hydrogen. Now we are looking for mass of sodium. So those are the two that we will relate. In order to relate those two, what we will use is the molar ratio. So what we have is 1 mole of hydrogen is produced when 2 moles of sodium are reacting. Or if 2 moles of sodium are reacting, then 1 mole of hydrogen is produced. So again, what we have is we have 2 ratios, the ratio 1 and the ratio 2. And we want to move to sodium, so we will use ratio 2 because we need to cancel out the moles of hydrogen. 2 moles of sodium. So moles of hydrogen and moles of hydrogen are cancelled out. And what do you have up to here is moles of sodium. And now, we don't need the moles of sodium. We need the grams of sodium. So this is where the molar mass is used. And the molar mass of sodium is, from your periodic table, 22.99 grams per mole. So 22.99 grams of sodium is 1 mole of sodium. Or if we have 1 mole of sodium, then we have 22.99 grams of sodium. So again, we have two ratios, the ratio 1 and the ratio 2. And we have here as left moles of sodium. So we will use a ratio 1 to figure out the grams of sodium. And the ratio 1 is 22.99 grams of sodium is 1 mole of sodium. So moles of sodium and moles of sodium is cancelled out. And what do you have up to here is grams of sodium. This is what we need. This is what the question is asking us for. So 20.0 in terms of numbers, 20.0 times 1 times 2 times 22.99, the whole thing divided by 24.8 times 1 times 1, and the units are grams of sodium. After you enter this in your calculator, what you should have is 37.1 grams of sodium. So what is saying here in this question is saying that in order to produce 20 liters of hydrogen gas in SATP conditions, in this particular reaction, you have to use 37.1 grams of sodium. So what do you do here? From known, you move to the molar volume using the molar volume ratio, and then you use the molar ratio of known and unknown, and then you convert it from grams to mole using the molar ratio, molar mass, sorry. Now, next question is nitrogen and hydrogen reacts to form ammonia. What volume of ammonia is produced when 7.5 kilograms of hydrogen reacts at 450 kilopascal at 80 degrees Celsius? So that means that we do not have STP or SATP condition where we can use the 22.4 and 24.8 or those constant molar volumes. We have to calculate that value. But what we will do is we will use Stoich all the way through. So now, keep in mind that this is not STP and SATP condition. You know that it is not because the temperature and the pressure are not at STP and SATP conditions. So I will show you two ways on which you can do this type of problem. So nitrogen and hydrogen react to form ammonia. What volume of ammonia is produced when 7.5 kilograms of hydrogen reacts at 450 kilopascal and 80 degrees Celsius? So we'll start with, every time we'll start with a balanced reaction. So N2 gas plus H2 gas, or 3 molecules of H2, will give us 2 ammonium. And we will list what is given. So we have 7.5 kilograms of hydrogen, and in order to move from kilograms to moles, we will need the molar mass. And the molar mass is 2.02 grams per mole. And then what we are looking for is liters, but at certain conditions, which are not standard conditions. So it is 450 kilopascal and 80 degrees Celsius, which converted into Kelvin is 353.15 Kelvin. Okay, so now I will show you the first method in which you can do everything from using Stoich, so not step by step, and then I will show you a second method in which you can do it in like small steps. So you'll start with what is given, 7.5 kilograms of hydrogen. Let's convert it into grams. So 1 kilogram of hydrogen is 1,000 grams of hydrogen. We convert it into grams because we are dealing with molar mass. Okay? And why do we need to deal with molar mass is because we need to move from and using the coefficients 2 and 3. Okay, so now we'll use the molar mass 2.02 grams per mole. So 2.02 grams is 1 mole of hydrogen. It's 1 mole of hydrogen, or 1 mole of hydrogen is 2.02 grams of hydrogen. So we have two ratios, ratio 1 and ratio 2. So we'll use ratio 2 as 2.02 grams of hydrogen is 1 mole of hydrogen. So grams and grams of hydrogen is cancelled out. Now we have the moles of hydrogen. Okay, up to this point, we have moles of hydrogen. In order to move to what it is asking us, we have to use the molar ratio. So we have 3 moles of hydrogen is needed to produce 2 moles of ammonia. Or when 2 moles of ammonia are produced, 3 moles of hydrogen are used. So again, we have 2 ratio, ratio 1 and ratio 2. And in order to move 2 moles of ammonia, we will use ratio 2 because moles of hydrogen will cancel out. So 3 moles of hydrogen and 2 moles of ammonia in the numerator. So moles of hydrogen are cancelled out. And what do we have up to this point is moles of ammonia. This is where it starts to the method that you can do all in one Stoich. So now we have those non-standard conditions with 440 kilopascal and 353.15 Kelvin, which means that we will use the ideal gas, or PV is equal nRT. So we start with the R value that is 8.314, and the units for it are kPal over mole K. Okay, so now mole, and it's moles of any gas. So in this case, so we will identify it as moles of ammonia. So moles of ammonia and moles of ammonia are cancelled out. And what you are ending up here is kPal over K. So now let's start cancelling out the units using the information that the question is giving us. So we'll start, we'll cancel out first Kelvin. So we have 353.15 Kelvin over 1. Why over 1? Because we always multiply with a ratio of 1 using different units. And now we are ending, so up to here, what did we have is kPa over Kelvin. And what do we have up to here is kPa. Now let's cancel out the pressure, kilopascal, and we go 1 over 450 kilopascal. So kilopascal and kilopascal is cancelled out. What we have at the very end is liters of ammonia, and this is what we are looking for. So in terms of the numbers, what do you have is 7.5 times 1,000 times 1, which we don't write, times 2, times 8.314 times 353.15 times 1, which we don't write again. The whole thing is divided by 1 times 2.02 times 3 times 450, and the units are liters, and this is what we are looking for. And at the end, you will have 1.62 times 10 to the power of 4 liters of ammonia. And if I'm asking you to record this into your in the form A.BC times 10 to the power of D, you will record only the digits. So you will have 1,624 liters of ammonia. Now the second method, it's exactly the same as when up to the red one, the red starts. But then what you will do is you will go like this. The second method is 7.5 kilograms of hydrogen times 1 kilogram of hydrogen is 1,000 grams of hydrogen. So kilograms and kilograms is cancelled out, times 1 mole of hydrogen is 2.02 grams of hydrogen using the molar mass. So grams and grams is cancelled out, and you will have moles of hydrogen. Okay, but then now we will move to moles of ammonium using the molar ratio. So 3 moles of hydrogen is used to produce 2 moles of ammonia. So moles of hydrogen and moles of hydrogen is cancelled out. And then you have 2,475 moles of ammonia. And then you take this and use the ideal gas law. Ideal gas law, 2 PV is equal nRT to find V as nRT over P. And then you go 2,475 times 8.314 times 353.15 over 450. And you will have volume of 1.62 times 10 to the power of 4 liters. So if you feel overwhelmed by the first method, then go ahead and do the second method. It's fine, it should give you the same result. So example 3 is saying that what is the volume of oxygen at STP condition needed to completely burn 15 grams of methanol in a fondue burner. So let's write the balanced chemical reaction first. So we'll have 2CH3OH plus 3O2 will give us a completely burn, means that is a full combustion. So we'll have carbon dioxide, and water. So what is given here is 15 grams, and now I will write the molar mass as well as 32.05 grams per mole, and we are looking for volume, liter, in STP conditions, which means that we'll have 22.4 liters per mole is a molar volume. So we'll start with what is given, 15 grams of CH3OH times, in order to find the moles, we will use the molar mass. So 32.05 grams of CH3OH is 1 mole of CH3OH. So grams and grams is cancelled out. We'll move now to the grams or moles of unknown, and we'll use the molar ratio. So will be 2 moles of CH3OH is 3 moles of oxygen. So the moles are cancelled out, times, now we are dealing with the STP conditions. So we'll use the molar volume as 1 mole of oxygen is 22.4 liters of oxygen. So moles and moles are cancelled out. And we will have at the end, in terms of numbers, 15 times 1 times 3 times 22.4 over 32.05 times 2 times 1, and the units are liters. And then that means that will be 16 liters of oxygen produced. This is on STP. If it was on non-standard standard conditions, then you have, again, 2 options, either to go full Stoich or to find the molar mass, the moles, and then use the ideal gas law to find the volume. Okay. Next example is an Albertan home is heated with methane. A home consumes 2.00 kiloliters of natural gas during month of December. What volume of oxygen at SATP conditions is required to burn this methane measured at 0 degrees Celsius and 120 kilopascal? So again, we are not dealing with the standard solution or standard solutions, either STP or SATP, because we have 120 kilopascal. Now we'll start with the, I actually will do it on another page. So I will start with writing a balanced chemical reaction. So CH4 plus 2O2 will give us, so we are assuming here that is a full combustion, so carbon dioxide and water is produced. So now what is given is that we have 2.0 kiloliters. You can straight go 2,000 liters of methane, but you can even do that. And then we have temperature is 0 degrees Celsius, which is 273.15 Kelvin, and pressure, is 120 kilopascal. And what we are looking for is what volume of oxygen, so liters of oxygen at SATP conditions are required. Okay, so SATP conditions have a molar volume of 24.8 liters per mole. So we'll start with what is given. 2.0 kiloliters. Let's convert it into liters. In 1 kiloliter, we have 1,000 liters. So kiloliters and kiloliters is canceled out. Now keep in mind, when we talked about this, the R constant in a gases unit, the R constant is 8.314 kcal over mole K. So those are the units. Now, if we are writing it as 8.314 kcal over mole K, then we cannot cancel the liters here, volume here. So therefore, we will not do that, okay? So we will write it as liters being the units of liters being in the denominator. So 8.314 kcal, and then we will have in the numerator, we'll have mole K. So liters and liters are canceled out. And then, since we are dealing with non-standard conditions, and then we have kilopascal to cancel out. So we will use the kilopascal in the top, so 120 kilopascal. So kilopascal and kilopascal is canceled out. You are ending up here with moles times temperature. So let's cancel out the temperature. And the temperature is 273.15 Kelvin, which 273.15 Kelvin. So Kelvin and Kelvin is canceled out. Now we have the moles of methane, and they are all methane. Okay, so this is CH4, CH4, CH4. All of them are moles of CH4, CH4, CH4. Everything that we are dealing up to this point is CH4. So what we have up to this point is moles of CH4. Now, since we have the moles of CH4, in order to find the moles or to move to the unknown, we will use the molar ratio. And the molar ratio is 1 mole of CH4 methane is needed to react with 2 moles of oxygen, so that carbon dioxide and water is produced. So then the ratio will be moles of CH4, which is 1 mole of CH4, is reacting with 2 moles of oxygen. So moles of CH4 is canceled out. What do we have up to here is moles of oxygen. And now we are looking for liters or volume of oxygen at SATP conditions, which has a molar volume of 24.8. So now 1 mole of oxygen is occupying 24.8 liters of oxygen. So moles of oxygen and moles of oxygen is canceled out. And then you are ending up here with liters of oxygen. And this is what we want. In terms of numbers, what do we have is 2.0 times 1,000 times 120 times 1 times 2 times 24.8, the whole thing divided by 1, which we don't write, 8.314 times 273.15 times 1 times 1, and this will be liters of oxygen. And what you will have is 6,038 liters of oxygen, or 6.04 kiloliters of oxygen produced. So this method is when we use Stoich all the way through. However, what you can do is you can do it step by step. If this is too overwhelmed, then you can do it step by step. So you can use ideal gas law. And then you will go PV is equal to nRT. And from here you'll find the moles of methane. So it will be PV over RT. So in our case will be 120 kilopascal times the volume is 2,000 liters over 8.314 kcal over mole K times 273.15 Kelvin. So kilopascal and kilopascal is cancelled out. Liters and liters is cancelled out. Kelvin and Kelvin is cancelled out. And you are ending up with 122 moles of methane. And then you take this and use the Stoich. So 122 moles of methane times the molar ratio. 2 moles of oxygen is 1 mole of methane over 1 mole of methane times 24.8 liters of oxygen is when we have the SATP conditions. So moles of oxygen is cancelled out, and then you will end up with 6,038 liters of oxygen, or 6.04 liters, kiloliters of oxygen. It's the same numbers, same answer, but this is one step, so going through the whole thing, and this is doing it step by step. Both of them are fine. I'm good with everything that it fits you. Best example for gases is ammonia reacts with sulfuric acid to form fertilizer, which is known as the ammonia sulfate. What mass of ammonia sulfate can be produced from 85 kiloliters of ammonia at 10 degrees Celsius and 100 kilopascal? Again, this is not standard conditions, so not STP, not SATP, where we know the molar volume. So we will start with the reaction, but I will do it in another page since there is a lot of. So we'll start with balanced reaction. So we have ammonia, so 2NH3 plus sulfuric acid will produce NH4 2. This is the fertilizer. Okay, it's the type of reaction that we are dealing here is formation. Okay, so again, I will do both methods, the one that you do Stoich all the way through and the one that you do that step by step. So the very first one is using ideal gas law. Why are we using ideal gas law? Because we are not in standard solution. Now, what is given here is 85 kiloliters, and we are looking for the mass, grams of this. Okay, So in order to find the grams of this, we need to know the molar mass. So I will calculate it right away and enter that information here, grams per mole. Okay, so now we'll use the ideal gas law, which is PV is equal to nRT. So from here, the moles of ammonia will be PV over RT. So in our situation, the moles of ammonia, using the information that we have here, that the pressure is 100 kilopascal and temperature is 10 degrees Celsius, which means is 283.15 Kelvin. We can say that the moles of ammonia will be 100 kilopascal times volume is 85, so 8500 liters over R is 8.314 K pal over mole K times temperature is 283.15 K. So temperature is cancelled, kilopascal is cancelled, liters is cancelled, and then you are ending up with moles, which based on the calculation will be 3611 moles of NH4 at 3. So, and now you take this information and you apply simple Stoich. So you go 3611 moles of NH3. To move to the unknown, we will use the molar ratio. So 2 moles of NH3 is used to produce 1 mole of ammonium sulfate, 1 mole of NH4SO4. So moles and moles are cancelled. And now using the molar mass, so 1 mole of NH4 SO4 is 132.15 grams of NH4 SO4. So moles and moles are cancelled, and then you are ending up in terms of numbers 3611 times 1 times 132.15 over 2. And then the units are grams of NH4 to SO4. And the answer should be 239 kilograms of NH4 to SO4. But you can do this as a simple Stoich, like 1 Stoich from the beginning to the end. So again, you start with a reaction. I will rewrite it. So 2 NH3 plus H2SO4 is NH4 2 SO4. Okay, what is given is that we have 85 kiloliters, liters, and then we have the temperature is 283.15 Kelvin, and the pressure is 100 kPa. Okay, and we are looking for kilograms or grams of this, knowing that the molar mass is 132.17 grams per mole. So we'll start with what is given. 85,000 liters of ammonia, NH3, times, now we are dealing with R value. So our value is, I will write it here, our value is 8.314 kcal over mole K. If we are writing 8.314 at the numerator, then we cannot cancel the liters because both of them will be in the numerator, so we cannot cancel it. So we will write it in the denominator over mole K. So liters of NH3, they are all NH3 is canceled out. Now we have pressure in the denominator. So we will use the value for the pressure, but in order to cancel it, we need to have it in the numerator. So pressure kcal is canceled out. Now when we see this, that is 1 over something over mole K, that is the same as having this term, mole K, in the numerator. So, okay. So now, just for simplicity, okay. So now we have to cancel the temperature. So temperature is the numerator, we will write it in the denominator. 283.15 K. So numerate K and K is cancelled out. What do you have now is moles of NH3. And then now since we have the moles of NH3, we know how to move to moles of ammonium sulfate using the molar ratio. So will be 2 moles of NH3 is 1 mole is needed to produce 1 mole of NH4,2SO4. So moles and moles are cancelled out. And we'll continue with the molar mass as 1 mole of NH4,2SO4 is 132.15 grams. So moles and moles of ammonium sulfate is cancelled out. And what do you have here is grams of ammonium sulfate. And this is what we are looking for. So now in terms of numbers, what do we have is 85,000 times 1 times 100 times 1 times 1 times 132.15 over 8.314 times 283.15 times 2 times 1, and the units are grams of ammonium sulfate, NH4,2SO4. And you should have the same answer as 239 kilograms of NH4,2SO4. So both methods are fine. You can use whatever you feel more comfortable with. This concludes the gas Stoich part of the lesson, and we will continue with the third one, which is the solution Stoich.